The utilization of drones has recently gained traction for aiding and performing a disaster relief mission. In this demo, we showcase the work that we have done in the 5G Dive project, building an autonomous drone scout system that leverages the 5G communication system, intelligent engine, as well as the edge computing infrastructure. The utilization of 5G communication allows for more efficient data collection and transmission from the drones to the edge. Combining both the 5G communication and the edge, our system will be able to perform cognitive processing and intelligent decision-making. With that said, the goal of our system is to perform person in need of help or PIH detection. The detection will allow us to identify and locate for PIH in a disaster-impacted area in real time. In our scenario, we categorize PIH as a person who is holding and waving a flag. The architecture and workflow of our system are as follows. From the DAS, we retrieve the datasets containing person and flag object. These datasets are what will be used by the IESS to train the dual object detection model. After training, the trained models are returned to the bus. The bus then deploys worker application via the OCS. Also, the bus is able to horizontally scale the deployed worker applications according to the system workload and measurements reports that is coming from the EFS. The OCS will then allocate resources and instantiate the worker applications within the EFS in response to the bus deployment specification. Then, the drone video stream and GPS are transmitted to the DAS for data preprocessing and storage. Eagle-Eye software components in the EFS then subscribe to the preprocessed drone data in the DAS. After that, Eagle-Eye EFS components will perform PIH detection and outputs PIH information. The PIH information that includes the bounding boxes and GPS location is exposed to the service platform. Then, Drone Navigation Server and the mission dashboard subscribe to the PIH information in the service platform. After calculations, the Drone Navigation Server sends waypoints to the drone for trajectory update. Operator in the command center will also be able to view the mission progression via the mission dashboard. Upon receiving the waypoints, the drone automatically adjusts its trajectory to provide a better view of the located PIH. In multi-drone deployment, different imagery angles can be obtained by autonomously navigate and coordinate drones at the disaster area. The Eagle-Eye EFS components continuously send computing latency reports to the DAS. For the demonstration, we set up our system as follows. We have the drone that is carrying the 4G 5G CPE. The CPE will connect to the small cell that is installed outdoor. On the other end of the small cell is the Edge Data Center. In the Edge Data Center is where all the applications like IMAC, EPC, Eagle-Eye, and Drone Navigation Server resides and run. Eagle-Eye itself is built on top of YOLO V3 object detection algorithm. We train and edit our custom algorithm to allow for the detection of PIH. With the use of pipelining and parallel computation techniques, as well as Opton's data center architecture, we were able to provide a real-time detection of PIH. Now, we will first take a look at the output of the system. To the right of the screen is the raw video that is captured by the drone. To the left of the screen is the output of Eagle-Eye. In the bottom left of the screen is the current GPS location of the drone and the detection status of PIH. When a PIH is found, a box will be drawn around the PIH. Here's a recorded video detailing the mission progress. After connecting the drones to the 4G network, the drone operator will fly Drone 1. During flight, Drone 1 will perform automatic scouting to search for PIH. While scouting, Drone 1 will continuously stream live video to Eagle-Eye that is run on the edge. Here, Eagle-Eye will detect for PIH. Once a PIH is found, its GPS location will be recorded and sent to the Drone Navigation Server. Finally, the drone navigation server will calculate new waypoints and send it to Drone 2 for automatic navigation to the PIH location to gather more information about PIH. We also did a benchmark to show the baseline network performance during the demo. In this benchmark, we set up a smartphone as a client. This smartphone is connected to the 4G communication network. We perform a ping test to measure the latency and iPerf3 test to measure the throughput. For the ping test, we get an average of 64.5 millisecond latency with a deviation of 23.4 milliseconds. As for the throughput, we get an uplink throughput of 19.5 megabit per second and 27.1 megabit per second of downlink throughput. This demo is to showcase the collaborative effort between partners from the European Union and Taiwan. Together, we aim at proving the technical merits and business value proposition of 5G technologies in Autonomous Drone Scout or ADS vertical pilot. In the future, we will add 5G NSA solution and consider the auto-scaling capabilities of the intelligent system.